All right, let's dive into something you probably do dozens of times a day without a second thought: searching for text. Today, we're going to pull back the curtain on the elegant, powerful theory that makes it all happen. And trust me, it's way cooler than you think. I mean, really, have you ever stopped to think about it? You hit Control+F, type a word, and bam, instantly it's highlighted in a document that could have millions of characters. How on earth is a computer that fast? Is it just magic? Well, the answer isn't just raw horsepower. It's actually this beautiful concept from the world of computer science theory called a finite automaton. It's a simple logical machine designed to do just one thing, and do it perfectly: recognize patterns. So, before we can even start to build our little pattern matching machine, we've got to lay down some ground rules. We have to define the language that it's going to understand. And in this world, language means something very, very specific. It's all built from just a few simple pieces. First step is the alphabet. Now, don't think ABC. Here, an alphabet is just any finite set of symbols we decide we're working with. It could be the binary alphabet, just 0, 1. Or for our examples, we might use something simple like ABC. Think of them as the only Lego bricks we're allowed to play with. Next, we've got a string. So if the alphabet gives us our letters or our Lego bricks, a string is just whatever we build with them. It's just a sequence of symbols from that alphabet. So with a binary alphabet, 0, 1, 1, 0, 1 is a string. With an AB alphabet, ABA is a string. Makes sense, right? And finally, we get to the most important part: the language. A language is not every single possible string you could ever make. Nope, it's a specific set of strings that follow a rule that we care about. So when you search for the word theory, the language you're creating is just the set of all strings that happen to contain theory. It's the collection of patterns we actually want to find. So let's put it all together right here. Let's say our alphabet is just A and B. We can make all sorts of strings, like AB or BB, but the language we're interested in might be, say, the set of all strings that start with an A. Our entire mission, then, is to build a machine that can look at any string and tell us instantly, yep, that one's in the club, or nope, not this one. Okay, so we've got our language rules down. Now let's meet the machine that actually does the work. This is the star of the show, the deterministic finite automaton, or DFA for short. The most important word to focus on here is deterministic. This machine never has to guess. It's like a train on a track where there are no switches. From any given station with any given signal, there is one and only one track to take to the next station. It follows a perfectly predictable path every single time. Here's how it all plays out. The machine is sitting at its starting station. It reads the first letter of our string, that's the signal. That signal tells it exactly which track to take to the next station. Then it reads the next letter and moves to the next station, and so on. If, after the very last letter, the train is sitting in a special accept station, then hey, the string is a match. If it ends up anywhere else, nope, it's rejected. Simple, super efficient, and perfectly predictable. So the DFA is pretty strict, right? It follows one single path, no deviations. But what if our machine could be a little more flexible? What if it could explore multiple paths at the exact same time? Well, let's meet the DFA's more adventurous sibling, the nondeterministic finite automaton, or NFA. The big giveaway is right there in the name, nondeterministic. When an NFA reads a symbol, it might have a choice. It could go to several different states at once. It can even jump to a new state for free without even reading anything. You can kind of think of it as being able to clone itself to explore every possible path all at once. This table really breaks it down. A DFA is like a methodical inspector, carefully checking one single path. The NFA, it's like a whole team of scouts, spreading out to check every path simultaneously. And what's really interesting is that even though the NFA seems way more complicated in how it operates, it's often a lot easier for a human to design one. They're just more flexible. So you're probably thinking, okay, this NFA that can split off and explore multiple realities has to be more powerful than the rigid, boring old DFA, right? Well, here is the mind-blowing twist of automata theory. It isn't. They are computationally equal. Anything an NFA can find, you can always build a DFA to find the exact same thing. The only catch? That DFA might have to be a lot bigger and more complex. All right, so drawing all these diagrams with circles and arrows is fantastic for understanding the theory, but let's be honest, that's not how anyone actually codes. So how do we tell a computer to build one of these machines for us? We use a super powerful shorthand that you've probably heard of: regular expressions. A regular expression, or regex, is the bridge between the pattern we want to find in our head and the automaton that actually goes and finds it. It's a compact little language made specifically for defining patterns. In fact, when you type into that CTRL plus F box, you're often using a simple version of regex, and behind the scenes, that expression gets compiled directly into one of these finite automata.
And this is where it all clicks into place. Instead of drawing a big, complicated diagram, we can just write these little patterns. A star means match the letter A 0 or more times. A or B means match either an A or a B. All of a sudden, with just a few special characters, we can describe some incredibly complex patterns in one tiny line of text. This is the engine inside your search box.
So these finite automata are amazing. They're the backbone of so much of what we do. But they aren't all powerful. And it's just as important to understand what they can't do to really see the limits of their logic. I mean, we've seen they can handle some pretty tricky stuff, right? Sequences, options, repetitions. But are there patterns out there that are just too complex for this simple state-by-state model to figure out? Well, there's a formal mathematical proof called the pumping lemma that gives us the definitive answer. Now, we are not going to get into the nitty-gritty of the math, but its conclusion is profound. And the answer is no. They absolutely cannot solve every pattern matching problem.
So what kind of patterns are off limits? Take a look at these. A language where you have to have the exact same number of zeros and ones, or a language of perfectly balanced parentheses. To solve these problems, a machine needs to be able to count and remember. It has to remember how many open parentheses it saw to make sure they all get closed. And here's the crucial point. A finite automaton has no memory. It only knows what state it's in right now. It is fundamentally, beautifully forgetful. So the elegant, memoryless machine that powers your text search is defined by its greatest strength, which is also its greatest weakness. It has no memory. And that leads us to our final big question. If the limit of this machine is that it can't remember, what happens when we build a machine that can?